Hello everyone, and welcome back. Today we're looking at a problem that isn't strictly probabilistic, but is based on a powerful technique widely used in quant interviews and puzzle solving. It's a method that shows up in a surprisingly wide range of challenges, from simple brain teasers to advanced mathematical problems. Let's jump right in and take a look at today's question. We start with an 8x8 chessboard colored in the usual alternating pattern. At any step, you are allowed to choose one entire row, one entire column, or any 2x2 square, and flip all the colors inside it, turning every black square into white and every white square into black. The question is it possible to finish with exactly 63 white squares and just one black square? Before diving into the full solution, let's take a moment for a quick warm-up. In a real interview, it's very common to brainstorm out loud and explore simple transformations of the problem. This helps us build intuition and get comfortable with the rules we're working with, while also giving the interviewer a clear sense of how we think, how we test ideas, and how we approach a problem before committing to a formal argument. One of the first patterns that naturally comes to mind is the possibility of turning the entire chessboard white. To do that, we start by selecting the 4 columns highlighted in red, and we flip their colors. After this move, we obtain the board shown here, where each row is now either completely white or completely black. At this point, we simply select the 4 black rows and flip their colors. And this gives us exactly what we wanted: a fully white chessboard. The theoretical background we need today is actually quite simple. But, as I mentioned at the beginning, it turns out to be extremely powerful. We're going to talk about a fundamental idea in problem solving, the mathematical invariant. An invariant is a quantity, a property, or a characteristic of a system that does not change under a given set of allowed operations. Even though the system may evolve or be modified, an invariant remains the same throughout the process. We constantly use invariants in mathematics. For example, the sum of the angles in a triangle is invariant under Euclidean transformations. The Lebesgue measure is invariant under translations in Ornithinet. The variance of a probability distribution is invariant under translations of the real line, and the homology groups of a topological space are invariant under homeomorphisms. Even though invariants, as we've seen from these examples, can be quite sophisticated and come in many different forms, one of the simplest and most powerful invariants can be parity, meaning whether a certain quantity stays consistently even or consistently odd. For example, adding 2 to a number preserves its parity. X is congruent to x plus 2 modulo 2. In this case, the parity is invariant under this particular operation. On the other hand, adding 1 to a number does not preserve parity. X is not congruent to x plus 1 modulo 2. Let's now see how we can use this technique to answer our original question. Let Wn denote the number of white squares on the board after the nth move, with W at time 0 equals to 32. We want to understand how this number behaves under the operations allowed in the problem. Suppose that at step n, the board contains Wn white squares, and at step n plus 1, we decide to flip the colors of some column. If that column initially contains k white squares, then it contains 8 minus k black squares. In the figure we have, for example, k equals 3. After flipping the entire column, it will instead contain 8 minus k white squares and k black squares. So we have Wn plus 1 equals Wn minus k plus 8 minus k. Since 8 minus 2k is always an even number, we conclude that Wn plus 1 is congruent to Wn modulo 2. In other words, flipping an entire row or an entire column does not change the parity of the total number of white squares. Now let's see what happens when we flip the colors of a 2x2 square. Suppose again that at step n the board contains Wn white squares, and at step n plus 1 we decide to flip the colors inside some 2x2 block. If that block initially contains k white squares, then it contains 4 minus k black squares. In the figure we have, for example, k equals 1. After flipping the entire 2x2 block, it will instead contain 4 minus k white squares and k black squares. So we have Wn plus 1 equals Wn minus k plus 4 minus k. Since the expression 4 minus 2k is always an even number, we conclude again that wn plus 1 is congruent to wn modulo 2. In other words, flipping any 2 by 2 block also does not change the parity of the total number of white squares. We have now shown that the parity of the number of white squares is an invariant of the problem. Since the board starts with 32 white squares, an even number, every configuration we can reach must also contain an even number of white squares. Therefore, a board with 63 white squares and a single black square is impossible to obtain. Thank you for watching. If you enjoyed this problem in the way we approached it, feel free to subscribe to the channel for more videos like this. And if you like problems based on invariants, there are countless fascinating variations out there, so if you'd like to see more of them, just let me know in the comments. See you in the next one.